We'll start the real recording now. First of all, 6033 in the news. So one of you, maybe on Zoom, definitely a student put this on Piazza. Um, I think yesterday, yeah, yesterday, could have been the day before, about beavers shutting down the town's internet for 36 hours after chewing through and stealing cables to build a dam. All right, so that is an exciting piece and an interesting piece of news. This is not the first time that nature has come for the internet. So sometimes sharks attack undersea cables. So one thing that you should know about the internet is that there are actual physical cables that run underwater. So there are cables under the oceans. There are cables in other shallower bodies of water, and sometimes sharks get to them. But it's interesting to think about kind of these cables. So this is not a graph I'm intending you to take a ton away from, but what I thought was interesting is that a lot of the data that gets sent across these undersea cables now is coming from content providers. So companies like Microsoft, Google, Facebook, Amazon, rather than sort of just existing as the internet backbone. And the reason that I think all of this is worth mentioning is one, I mean, it's a little bit funny that beavers chew through a cable. It's a little bit funny that the internet gets attacked by sharks. But it is a real thing to think about when we build these systems, they impact the environment, right? Internet cables run through nature, right? When we put wireless sensors everywhere, they are in nature, right? And so sometimes, things like animal attacks can happen to them, but it is also worth thinking about, what does it do to those environments, right? Like what does the physical infrastructure do to those environments? So that is just a thing to think of. And it was brought to mind by knowing that beavers shut down a town's internet for a pretty long time, like a day and a half, because they needed to build a dam. Okay, so that's 033 in the news. Today, lecture 19, not lecture 18. That's also not the title. Wow, this is going well already. Let's find out what we're going to do today, though. All right, so this is where we left off last time. We had multi-site atomicity working, which if you think back on where we were in day one of fault tolerance, this is surprising, right? Day one, we weren't even sure we'd get atomicity on a single machine, and now we have it across machines. But we had this one lingering problem, right? And you can see it because it's here on the slide in the top right, right? In the last lecture, we imagined having like one server with A to M data and one server with N to Z data. And if any of those things went down, the data was unavailable, right? If the coordinator went down, the whole system was unavailable. We can recover from those failures. So that's not like an issue of, correctness or anything, but the unavailability is not great, right? That was our whole goal at the beginning, right? We wanted, you can see on the slide, to build reliable systems from unreliable components while keeping availability high. All right. So, the solution to this in some sense, right? The solution here is replication. We are going to replicate data. Right? What we're going to do in lecture is use replication and try to achieve single copy consistency. This is what, if you recall yesterday's recitation, this is what that paper referred to as strong consistency. Right? It's a property of the externally visible behavior of a replicated system. And what it means is that operations are going to appear to execute as if there's only a single copy of the data. Right? Internally, we're going to have copies of the data. That's what we want. That's what we want to keep availability high. But internally, there might be failures. There might be disagreements about like whether a write has completed or where it's visible. We have to figure out a way to mask that. Right? And you should be able to draw parallels between this set of things and when we were talking about serializability. Right? We talked about conflict serializability, a fairly strong form of serializability. There are more relaxed forms, right? In lecture, we're going to work on single copy consistency, right? But there are more relaxed forms. That's what you saw in yesterday's recitation paper. This is also what you've seen from DNS. DNS does not give us single copy consistency, right? There are all sorts of trade-offs here, right? There is no like single best consistency model. right? The best consistency model for you is the one your application needs. Some systems do need single copy consistency, all right? So I will teach you today how to get it, all right? So let's start with a basic setup. So remember last time we had a bank, we were doing transfers, and we're gonna start to replicate data, all right? So in this first attempt, we're not doing anything special. We're just trying to imagine what this system would be like take what we did last time, what would go on if we had multiple servers, right? Multiple copies of data. You can imagine how this might work. Okay, this is not what we're gonna go with, but you can imagine what we might do, right? We're trying to make this, bank transaction. You can imagine this coordinator sending, this update to all of the replicas, right? Subtract amount dollars from A on every server, right? And then, okay, do the transfer with the B. No, you can imagine how this might work, right? But let's expand it just a little bit because I want to illustrate one of the big problems that we would have to solve in this sort of system, right? If we're going to replicate servers, we're also going to replicate coordinators, right? So we can have 2 clients and 2 coordinators and 2 copies of the data, right? And imagine now we're going to do just even a simpler write. One client wants to write 20 to A, one client wants to write 30 to A. All right, well, those coordinators can pass those writes to the 2 replicas. But now there's a network in between. There's a lot of stuff happening. The timing could certainly be such that, one of these replicas says, okay, A equals 20 and then A equals 30. And the other replica gets A equals 30, A equals 20. Right, so it is super, super easy in a situation like this for these replicas to become inconsistent. And nothing's even failed, right? So we're gonna have to deal with this problem. This is sort of, there's all sorts of other things that would be wrong with this, but this is like the crux of what we have to address today. All right, so how do we do this? How do we ensure that the servers remain consistent? So the general approach to this problem is known as replicated state machines, or RSMs. And I'm going to give you we're going to go with our second attempt, which kind of gets us halfway there, but not quite. Okay, so here's a basic setup, which we're going to evolve, right? The basic setup is that instead of having just sort of multiple replicas that are all in some sense equal, we're going to designate one replica as the primary replica. Right, and almost all of our communication is going to flow through that primary replica, right? So again, the system, this isn't perfect yet. There's still going to be one problem with it, but let me show you the basic idea of how this would work, right? So notice, first of all, clients are communicating with our coordinator C here, right? So they're all talking directly to this coordinator, just like last week, just like Monday, which was not a week ago. It was a mere 48 hours ago, just like Monday, all right? The coordinator is sending any requests, right? Requests to update data to the primary server, right? Which on this picture is S1, right? It is the primary's job to do a couple of things. Its job is to choose the order of operations, choose whether A equals 20 goes before A equals 30, right? Or something like that. It is the primary's job to decide all non-deterministic values. All right, so let me give you an example of what such a value would be. Suppose that your transaction was like, A equals the current time, right? And you wanted S1 to read the current time. Okay, that is a non-deterministic value, right? So what A is going to do is going to read the current time, and then that, whatever timestamp it reads, that's the timestamp we're going to use on all of the replicas, right? So it's going to ensure all operations are deterministic in that way. I always, in my head, I often think about like the current time as a good example of a non-deterministic value, because it's a little bit harder to just imagine a scenario where like we just want someone to write random data somewhere, right? So imagine something like that. And so, how is this primary replica interacting with the backup, right? We want a notion of there is a primary server and a backup server, and we want them to remain consistent. Like that is our whole problem here, right? So the primary will only respond to the coordinator with, sort of an act, like with an okay, everything's good to go, after it's sure that the backup has all of these updates. All right, so if you're trying to say, okay, A equals 10, right? S1 will do that right. It will push the write to S2, wait for a response from S2, and then get back to C. All right, so when S1 tells C, hey, this write has gone through, it means it's gone through on every backup. Right? In these slides, I'm going to give you one primary and one backup. You could extend this to as many backups as you want. Right? There'd certainly be like it would cost you more money to buy more servers. It would be a performance hit to some extent. But if you want 10 backups, have 10 backups. It's fine. All right, I'm drawing one. All right, so this is some of the basic idea here. What would happen if there were a failure? Right? Suppose this primary server fails. This is in some ways, this feels like a very bad thing, right? The backup server could fail. That's not such a big deal, all right? The system will just continue on without a backup, right? Like it's bad for availability, but we'll recruit another idle server at some point to use as a backup. We'll get all of the data onto it. We'll get it working again, right? Dealing with a primary failure feels harder because the primary is important in a way that the backup is not quite as important. Right, so but let's see what happens. Effectively, C just needs to switch. It needs to go to the backup server and say, hey, you're the primary now. Right? And again, ideally, S1 recovers at some point, right? We get all the data synchronized, or again, we recruit an idle server. For the purposes of this example, though, we just want to make sure that C can correctly switch to this backup, right? We're going to operate on an assumption in this lecture that failures are independent, right? If our primary and our backup server went down at the exact same time, yeah, we do have some availability issues, right? And that can happen. It can happen because the beavers ate the cable that goes into the rack that both of those servers were sitting on. That can happen, right? Beavers come out of nowhere. There are some things that one can do about that, right? You can try to deal with non-independent failures, dependent failures, I guess we would say, by thinking about the physical placement of servers, right? Making them really geographically diverse, all of those sorts of things. It's challenging, but it can be done. But so in today's lecture, we're going to assume failures are independent. All right. Now, I told you that this setup was not going to get us all the way there. All right. But the primary failing, like that's not the problem. That's actually we're kind of okay with this. Let me show you the problem. All right. The problem that we still need to deal with is a type of failure that we haven't really talked about. Okay, so I'm going to spend just like a little bit of time explaining what this failure even means. But okay, we're in this world, we're replicating data across multiple servers. And I don't think I said this at the top. I should have said this at the top. When you think about our bank, right? We had an A to M server, we had an N to Z server, right? We're going to replicate both of those things, right? There could be 2 A to Ms, 3 A to Ms, 2 N to Zs, 3 N to Zs. We could even partition differently, right? Like A through G, etc. We're zooming in for this lecture on like a single partition of data. All right, so that's why we're just looking at this one primary, one backup. But okay, we're probably going to have multiple coordinators, all right? Because we cared about coordinator failure. We want to be able to scale. We want to be fault tolerant. So let's just imagine we have 2 coordinators, right? How would this work? Right. So like I've said on the slide, for a single transaction, a client would stick with the same coordinator. Okay, we're not going to have to do like weird coordination between the coordinators, ironically. So we've kind of partitioned our clients to different coordinators. In terms of how they would use this setup, just like we've been doing before, coordinator 1 communicates with the primary, so does coordinator 2, right? All of this would work fine. But here's the place where it can fail. We're going to keep all of the machines up. Okay, every machine, no machine fails in this example. The thing that's going to fail is the network. And imagine that the network fails in such a way that it partitions this system. So what I mean by that is that there are network failures such, So this is my partition. I've partitioned the slide for you, right? That means that machines on the same side of this line, they can communicate, right? So for instance, C1 and S1 can talk to each other. C2 and S2 can talk to each other, but they can't communicate across that line. All right, so those communications before go away. Right? And if you're looking at this, you're thinking, this seems so unlikely, right? It's unlikely in some networks, right? It's unlikely on the internet. It's unlikely for the internet to become partitioned because it is so robust. There are so many other paths to use. This can totally happen though in like a data center environment, right? There's a lot of thought put into how the network is set up. Like we don't want this to happen. This can happen. So let's imagine, okay, so what are these coordinators thinking, right? What's going on? Well, from C1's point of view, its backup has failed, right? It can't reach S2. If it can't reach S2, as far as C1's concerned, S2 has failed, right? There is no difference from a coordinator's perspective from a machine actually physically failing or from all of the network around the machine failing. If it can't reach the machine, it can't reach the machine, right? So it thinks that S2 has failed. It's going to keep S1 using S1 as the primary, right? There's no backup at the moment, which again, we know we'd want to recruit a new backup at some point, but this is where we are right now. All right. On C2's side, C2 starts to use S2 as the primary. It says, hey, the machine that was the primary, it's failed. This is the machine failure we saw before, right? The primary has failed, right? I'm going to use S2 as my primary. This is bad, right? Both replicas think that they are the primary. They are not checking with each other about these updates going through, right? They will very quickly become inconsistent. All right, so this is a big problem with the setup we have so far. Kate, I see in the question, is there a rule of thumb for how many replicas are needed for a system to be fault tolerant by a certain amount? That's a great question. I don't know that there is going to be a rule of thumb in general because it is so application specific. And it depends on like how much availability you want from different parts of your systems. Certainly, you know, different, we'll say like providers, different companies, whatever, would have targets that they want to reach, right? Like we want 99.99% availability, right? And then kind of stepping back from that, that might inform how many backups they have. You might also have, you know, people doing analysis on what types of failures are likely here, right? Like how likely is it for, say, both the primary and the backup to fail at the same time? And I would invite the rest of the staff, if anyone has specific examples, feel free to drop those in the chat while we continue on with our replicated state machines. All right, so this network partition, this is a challenge for us. And it's a particular challenge because in this setup so far, we have distributed the decision about which replica is the primary. Both C1 and C2 are making these kind of independent decisions. They came to different conclusions. Now there's sort of two primary replicas. They're going to be inconsistent. We don't want to do that. So we're going to keep this basic setup, but we're going to add one more component, right? Known as a view server, right? That's what VS stands for here, view server, right? Let me tell you just the basic idea of how this is going to work. So nothing's going to fail yet. I want you to understand like how communication runs in the system now. And then before we talk about specific failures, we'll do a little bit of like a moral examination of how we feel about the view server, right? But so here's how things are going to work. I've gone back to a single coordinator on the slide, right? There can still be multiple coordinators, right? And here's what they would do. So first of all, the view server is responsible for deciding which replica is the primary and which replica is the backup. And it keeps this knowledge in a table, which we would typically call the view table, right? And it maintains a sequence of views. So let me show you what a view is. It's just a line. It's just like a line in a database. This is view number 1. The primary is S1, the backup is S2. Right? We'll look at some different failures. You'll see the view change, but all it's saying is here's the primary, here's the backup. If there was another backup, it would be like, S1 is the primary, and then S2 and S3 are the backups. So it's keeping that small data structure. Right? Now, this is not useful if the replicas don't know which one of them is primary. Right? So the view server is going to tell them. Right? It's going to contact S1 and S2 and say, hey, S1, you are primary. S2, you are backup. They will act that, and then they will know. Right? And you can assume reliable transport where appropriate, right? Like if an ACK was lost, the view server would try again, that type of thing. Right? The relationship between the primary and the backup is just as we described. Right? That primary is going to push updates to the backup. It's not going to confirm an update until it hears from the backup. That's just like before. Right? Nothing has changed about the relationship between the primary replica and the backup. Right? So, how are we going to use this, right? Like, how does the coordinator sort of deal with this? Right? The coordinator is going to ask. It's going to ask the view server which replica is primary at this point, right? Instead of making that decision itself, it's going to ask, right? So ask for primary, the view server responds with S1. And imagine like a pretty fine-grained, maybe as fine-grained as we can make it. You can imagine the coordinator asking that like at the beginning of every transaction, right? Savannah, in the chat, amazing question. We're going to come to that in like 30 seconds. Why can't the coordinator do this itself? We'll talk about that in just a second, right? But so once the coordinator knows who the primary is, things proceed as before, right? It reaches out to the primary. Here are the updates. Primary pushes those updates to the backup, right? And responds to the coordinator, right? And then one last thing, which I have not made explicit up until this point, but you may have expected. You can assume that the primary and the backup servers, they're just constantly pinging the view server. That's how the view server is going to detect a failure here if it's not hearing from S1 or S2. This is just like a hello protocol, right? It's just constantly saying like, I'm here, I'm here, I'm here, I'm here. All right, so again, nothing has failed yet. This is the basic setup, okay? And literally, in my notes, at this point, the first question I have to ask is, why didn't we just add this view server functionality to the coordinator, right? The reason we didn't do that is, remember, we can have multiple coordinators. We actually, in some ways, had this functionality in the coordinators before, and we had it in multiple coordinators, right? We had like C1, we'll call it C prime, and like C double prime, right? If all of these coordinators are coming to their own independent decisions about which replica is the primary, that quickly is brought down by any sort of network partition, right? So what this means for you, and you should, I'm going to say a sentence, and part of you should be scared, right? There can be multiple coordinators, and there should be multiple coordinators. There can only be one view server. There is a single view server, right, for this partition of data. And the reason you should be scared is because that seems like a terrible idea. What if the view server fails, right? Yes, thank you, Johnny. Appropriate reaction, right? What if the view server fails? I've just created this like extremely centralized component. It's a legit question. It is a problem, and we will deal with it. Before we deal with it, we need to deal with some other stuff first, right? Here's some of the other stuff. Even if you don't worry about the view server failing, it feels like, oh my gosh, this one machine, we've given it so much responsibility and so much computation to do, potentially. Can it do all of this work? All right. So a couple of things to note. The view server only has to keep track of which replica is the primary. And it has to refer to some pretty lightweight requests from the coordinators. It is not, for instance, like performing rights. It's not deciding a global ordering of operations. So what it is doing is relatively lightweight. Second, though it may not be easy to replicate the view server, we'll talk about that later, we could distribute it, right? So we could have view server 1 that handles like the first partition of data. We could have view server 2 that handles the second partition of data, right? And what I mean by that is like view server 1 would handle the primary and backup, or backups if there are more, for the first partition of data, right? View server 2 could handle the primary and backups for the second partition of data. View server 3 could handle the primary and backups for the third partition of data. We would need a way to route coordinator requests to the correct view servers. That is doable. That does not solve our fault tolerance problem with the view server, right? But we could distribute this functionality across multiple servers, right? And then the third thing I want to point out to you, even though these systems are big, they're not internet big. The view server is not keeping track of like every machine connected to the internet. If you believe that the controller in MapReduce can work, you can believe that the view server can work. But again, what if the view server fails? All right, we'll come to that. So let's do some slightly less terrifying failures first. And as you can see, one of the things we're going to have to ask ourselves is, can this handle the network partition? That's what got us into this problem in the first place. If this can't handle a network partition, this lecture was a waste, right? All right, but we won't partition the network first. We'll have a machine go down first. All right, so let's imagine again the primary replica fails. That feels like a bad thing to happen. All right. In illustrating this failure to you, I'm going to give you a couple of other details about how this system works. Right, I will summarize all of the details of this entire replicated state machine for you at the end of lecture. All right, so there will be like a single slide that tells you everything. All right, so what's going to happen? Well, the view server will know it's not getting pings. All right, so it knows that S1 has failed. All right, it's going to update its view, right, and it's going to let the primary or the backup server know. It's going to let S2 know that it's primary. Right? Notice what this view table looks like. All right, it says now we have view 2. The primary is S2. There's no backup, right? Ideally, we'll get a backup again at some point. But for right now, we just want to make sure we switch over safely. Right now, what happens when C starts to communicate? All right, if C tries to communicate with S1, say it was like mid-transaction, right, and it was still communicating with S1, it's not going to get a response. S1 is legit down. It's not responding to any requests. So that transaction will presumably be aborted. Right? That's okay. Right? Now, when C next asks the view server who the primary is, the view server will say S2. Right? And certainly an inability to communicate with S1 would be a really, really good reason for the coordinator to go back to the view server and say, hey, give me an update about this. All right? So again, notice there's no longer a backup. Right? We'll bring it back up online eventually, but this is how we switch from primary to backup. Right? It's not totally unlike how this was working when we didn't have the view server. Right? The primary goes down, tell S2 that it's now the primary, and now requests go to S2. This is okay. This is not the most interesting type of failure. Right? Here is it. Oh, Julia, how often does the coordinator ask the view server who the primary is? Oh boy, so many questions. So you could imagine the coordinator, there's a lot of different ways that this could work. You could certainly imagine the coordinator asking the view server before any new transaction. So like always checking before a transaction. You could imagine, you could do some tweaks so that the coordinator asked less frequently, but sort of had some mechanisms to deal with certain types of failures. And actually we'll show kind of a good example in just a second of what's going here. What if the, Derek, amazing anticipation for lecture. As usual, you all in the chat could basically just run things. What if the connection between the view server and S1 fails, but the connection between C and S1 is still okay? What indeed? What indeed? Let's find out. All right, so here we are, everything's back up again, everything's very happy. We're back in view number 1, and we're going to have a network partition, and it's going to be different than before, right? What happens if a network partition prevents S1 from communicating with the view server? Right, here's how I'm going to draw that. It's like a shield, right? So this is in some sense the worst thing that can happen, right? So let me first make sure you understand why this is really bad. Because we're concerned about consistency, it is actually very bad for us if all of our machines are up, but if they don't agree, right? If one of them fails, like if one of them is actually totally offline, it's not going to get inconsistent because nothing's talking to, it's just not there anymore. It just disappears, right? We just have to fail over safely. It is worse for us if every machine is up and responding to requests, but they don't agree on what's going on. And here is a place where we can get into a disagreement, all right? Because what you can see here, from the view server's point of view, S1 has failed, right? It's not getting any communication from S1. That it's presumed that it's failed. That's all it can do. So the view server is going to try to switch to S2 as the primary. But C can still talk to S1, S2 can still, everyone else can still talk to S1. All right, before we got lucky. Like if C tried to push any updates to S1, S1 was down. It couldn't. S1 is no longer down. Okay, so let's see what's gonna happen. It's gonna be very exciting. I hope you are all appropriately hyped for this failure. I know that Johnny is hyped because he always gives me good reactions. Okay, so let's see what the view server is gonna do first. And I'm gonna kind of pause us like in the middle of the view server's action. All right, so first thing, the lack of pings again indicates to the view server that S1 is down. So it's going to do, the view server is going to do the same thing it did before. This is a failure of the primary replica. It needs to switch over to the backup. It's going to create this new view. Again, there's no backup right now from the view server's point of view. And it's going to let S2 know. But what I'm interested in first is what happens right before that. Right? What happens when the view server says, okay, S2 is the primary, but S2 doesn't know about it yet? Right? What's going on? Right? So first of all, if the coordinator isn't sending any updates, who cares? Nothing's happening on the system. It's only interesting if the coordinator is actually pushing updates. Okay, so let's imagine. So suppose the coordinator was still sending updates to S1. It was mid-transaction. It thinks S1 is the primary, right? S1 still thinks it's the primary. Those updates are actually, they're going to go through just as if S1 was the primary and S2 is the backup, right? S1 and S2 aren't going to get out of sync there, right? Again, you know, an update to S1 can't be ACT back to the coordinator until it's also on S2. So they're going to keep the same state, right? At this moment, they're not doing exactly what the view server expects them to be doing, but they're getting the same state. It's almost as if this particular operation happened before the network failed. Okay, so this is okay. Now imagine we have, maybe there's a second coordinator that comes in, or C has just started a new transaction and it learns from the view server that S2 is the backup before S2 itself knows that it's the backup. All right, this could be problematic, right? If C starts pushing updates to S2 and they're not reflected, like that could get us into trouble. Here's one detail. S2 will reject that. S2 still thinks it's the backup. If it gets messages from a coordinator, it just says, no, thank you. I cannot push that update for you. I am not a primary replica, right? In this situation, right, even though the view server thinks S2 is the primary, our replicas are still gonna maintain consistency, right? They're it's going to be just as if S1 was a primary and S2 is a backup, because S2 is going to reject requests from anyone that thinks it's the primary. Right? So S2 is going to maintain its role as the backup. Right? And again, this is okay. Right? Again, imagine this system working. It's just as if these updates had come through before the network failed. Right? Everything is happening fine. Now, what about once S2 knows it's the backup? Or sorry, once S2 knows it's the primary, it's no longer the backup. Now, like on this diagram, this looks like we could be in trouble. I've colored 2 boxes blue, right? It looks like there's 2 primaries. So again, what's going to happen? Right? Well, as before, this is not interesting if the coordinator isn't doing anything. If there's no updates going through the system, nothing's going to change. So nothing's going to get inconsistent. Right? So again, suppose that our coordinator were to send an update to S1. Right? It might be in the middle of a transaction. That can still happen. It can still talk to S1. But now S1 isn't going to get an ACK from S2 because S2 no longer thinks it's the backup. S2 thinks I'm the primary. As backup, it rejects those requests. I should have highlighted that on the slide. I'll make sure to highlight that on the final version of the uploaded slides. All right. So once S2 believes it's the primary, it no longer acts as a backup. And because S1 can't do an update unless S2 says, yes, I also did it, any requests that the coordinator sends to S1, they're just rejected. They don't go through, right? And again, it's not because S1 is down. S1 isn't down. So you can still totally talk to S1. It's not because the network between S1 and S2 has failed. It hasn't. They can talk to each other. It's because S2 understands its role as a backup, and as a primary now, and its previous role as a backup. Right? And it says, I'm not your backup anymore. I don't act this request. All right, so now, if S2 starts to get requests from the coordinator, which it should, right? Then it goes ahead. It updates, right? It does the updates. It knows it's the primary, right? It's moving on with this process of this data. All right, so the true moment of like this switch over occurs when S2 hears about view 2, right? When S2 learns it's the primary. That's the point at which we have switched, right? This keeps our servers in a consistent state. Now, I want to kind of bring this full circle for you, all right? Assume that S1, like the network repairs, it fixes itself, right? Maybe it was just like a really full queue or something. Anyway, it's back online. You might be tempted to think like, oh, won't S1 and S2 be out of sync now? S1 is no longer in the view, right? S1 has no part in this view anymore. And as soon as it is up, it will learn about that, right? Which brings us an important rule, right? If your machine is a primary in some view, it had to be a primary or a backup in the view before it, all right? So for instance, we can't do this. We couldn't say, oh, great, S1 is back. Let's go back to this view again. S1 isn't set up to be the primary. There's so many updates that it potentially hasn't gotten, right? It doesn't get to be the primary anymore, right? We can put it towards like the pool of idle machines that we might draw new backups for. We could work on getting the data from S2 pushed to S1 and bringing it back in as a backup, all right? But don't think that just because S1 comes back online, it gets to be the primary again. It does not. It's not up to date. It is not consistent with S2 at this point, right? Now, the gaping hole, right? We have multiple replicas of data. We have multiple coordinators, right? I'm only showing you one here, but again, you just envision additional boxes, right? There can totally be other coordinators. They all communicate with the view server. What if it fails, right? What happens if the view server fails, right? And the answer to this question is the greatest answer that I ever get to give in lecture, which is you go to recitation tomorrow. We will not solve this in lecture, right? But to kind of prep you for lecture, remember why we had the view server. The problem that we had was we needed a consensus on which replica was the primary. In our first setup, there were different machines involved in making that decision. There were multiple coordinators. If they came to different conclusions, immediately things got inconsistent. Having a centralized component here means that we don't have to come to an agreement. The view server decides, right? All we have to do is get people to ask the view server. However, in tomorrow's recitation, right, you're going to talk about a system called Raft, right? And what Raft gives you is a way to get distributed consensus. All right, so we could apply it here and have a distributed set of machines come to an agreement about who is the primary, right? And who are the backups. All right, so coupled with Thursday's recitation and next Tuesday's recitation, you will be very, very, very fault tolerant. Right, but again, let me give you, this is kind of all of the pieces of these replicated state machines, right, including the kind of details that I added before. Important things to note, that like a machine that thinks it's the primary will behave as the primary. A machine that thinks it's the backup will behave as a backup. A backup won't accept requests from a coordinator. That's not how the system works, right? A primary won't complete a request if it can't get its backups agreement. Right, so they're going to act as their roles indicate that they should act, right? Now, what does this mean for you? We are pretty fault tolerant at this point, right? How did we get here? All right, so we spent a long time talking about transactions, which is really this abstraction that makes it easier to deal with failures and currents. I see, Kara, I'm dropping out a little bit now and then. I do not know how to fix that. But the recording should be okay, hopefully. We're gonna make it through the semester. We're gonna be fine. We'll be fine. So I hope not. Although I would love to see a beaver around here. We have a fox in my neighborhood right now, which is the talk of the town. It had babies, so there's also baby foxes. So we've talked about transactions, and most of what we've done in lecture is get them to work. How do we get atomicity? How do we get isolation? You should see a couple of themes. One, there are a lot of decisions about how much fault tolerance to have, right? What type of serializability do you want? What type of consistency do you want, right? There's not a single best one. And what you can also see now is getting fault tolerance, it adds complexity, right? It's essentially inevitable, because typically if we want fault tolerance, we need to write a piece of data into more than one place, right? Once we are writing something to two different places, all sorts of bad things can happen. They can get especially bad if there's a network between the two places. And if you move towards fault tolerant systems that try to be fault tolerant even to like non-independent failures, so things like natural disasters and stuff like that, one way to do that is to spread your data across the globe, or like at least, across the country or something like that. Even more complexity, right? But so where are we going to go from? Oh, and the last thing I want to say before I tell you where we're going. Remember when I told you at the beginning of this section, how designers plan for failures matters, right? We can't live in a world where systems can fail in like all sorts of ridiculous non-atomic, non-isolated ways, right? Making these choices is important because it affects the types of guarantees that you can give your users. It affects their access to like their, banking information and things like that. Like there have been instances where a company stores data in a couple of data centers, and one of the data centers goes down, and now people can't access money, right? They can't access all sorts of things, right? So making these decisions, they can feel very, very technical, like replicated state machines. Realistically, you're not going to like walk around and just run into a replicated state machine, right? But how you decide what types of fault tolerance to apply is a huge impact on the people who are affected by your system. right? So where we are going after this is the end of the fault tolerance part of 033. Starting next week, we're going to still fail things, but we are going to look at more targeted and often malicious attacks. So we're going to look at sort of different ways that systems can be attacked at all levels. We'll sort of look at like within an operating system, then within a network, then within more distributed systems. We'll figure out how to uphold some goals even in the face of those attacks, right? So that is where we are headed. So real quick, I'm gonna stop recording